LOFTID project, and I put this together in conjunction with Dr. Neil Cheatwood, who's the principal investigator for LOFTID. And we principally put this together, but there's a whole team of literally hundreds of people, so that contributed to this. So they couldn't all fit on this page, so I just kept it at me and Neil. So I'll give you a quick overview of HIAD. So HIAD stands for Hypersonic Inflatable Aerodynamic Decelerator. And this is a deployable aeroshell technology consisting of two main elements. And you can see the elements in the images on the right side of the slide. The inflatable structure is a heat-resistant, sufficiently rigid structure for maintaining the shape during entry. And it can withstand significant aerodynamic forces. The flexible thermal protection system shields the inflatable structure and protects the vehicle from the extreme aero heating and shear environments associated with entry. So on the right side, you see the inflatable structure at the top, the flexible thermal protection system, which we refer to as the FTPS. And then the bottom picture is those two items integrated together as an aeroshell. So what HIAD is important for, they can be hard packed, allowing them to be stowed into a small volume at launch, much like a parachute, and then deployed prior to atmospheric entry to generate much more drag and decelerate much heavier payloads than conventional heat shields. In the image on the left, you can see that the current technology uses up every bit of the fairing and can only get to a diameter currently close to 5 meters. There are new vehicles now that'll take it up to on the order of 7 meters. But a HIAD can reach much larger diameters, and the name of the game is drag to be able to land heavy masses onto the surface of anywhere with an atmosphere, Earth, Mars, other bodies. And it also decelerates at a higher altitude. The reason that's important is currently, if you look on the right picture showing the topographical, that's the word I'm looking for, topographical map of Mars, you can see that our landing sites are all in a certain region that is what we consider below sea level at Mars. That is because with these current diameters of the heat shields, we can only generate so much drag. We need to use the full depth of the atmosphere to be able to land sufficiently, slow down and sufficiently to land. So currently, those areas in black are inaccessible to us. And with the HIAD, or with a large diameter aeroshell, you slow down much sooner and get to those descent and landing operations at much higher altitudes. That'll enable much more of the surface of Mars to be explored. So LOFTID was a HIAD technology demonstration. It was a 6-meter diameter aeroshell that was inflated into orbit and re-entered to demonstrate the HIAD technology at a larger scale than has ever been done before. And it is at entry conditions that are relevant to Mars and Earth mission applications. LOFTID launched on a ULA Atlas V rocket as a ride share, one of the largest ride shares they've ever done. And it launched out of Vandenberg Space Force Base on a polar orbit, with the primary mission being the JPSS-2 satellite. So in that lower picture, you can kind of see the launch configuration. They had to use an extended payload fairing to fit what we called the super stack underneath the fairing on top of the Centaur. And the primary payload sat on top of a extended payload adapter, and LOFTID was stowed within that payload adapter. So everything for LOFTID had to fit within that payload adapter. It stayed out of the primary load path for the primary mission. And then we had to have a system that separated that payload canister away from us so that we could deploy the HIAD and re-enter. Of note, this was an ambitious project. LOFTID was the largest blunt body aeroshell ever entered, and it entered at 8 kilometers per second and reached speeds over Mach 30 during entry. So the LOFTID architecture, this shows you how we stacked that super stack. So from left to right, the first thing we did was attach the payload adapter separation system that was developed by the LOFTID team. And that included halo springs and an inner shroud that mounted to the payload adapter canister and a netting system that allowed it to react force against the stowed inflatable aeroshell. And then we lowered the reentry vehicle into the lower portion of the payload adapter. And the reentry vehicle consists of the hard-packed aeroshell, which you see in the right picture, the forward segment and inflation system tanks, the mid-segment and avionics deck, and the aft segment, which included the ejectable data recorder, cameras, the beacons, and a parachute system. So all this fit within that payload canister, and as part of a do no harm for this mission, we had to make sure it was all contained and did not contaminate anything on the sensitive instruments for the primary mission. And the lower left shows the reentry configuration, where it's 6-meter diameter, nearly 2 meters tall, and the mass is 1,100 kilograms. So I'll go through the concept of operations. This is what takes place after the deorbit burn. So the primary mission was delivered to its orbit. Then they conducted a burn or contamination and collision avoidance maneuver. Then a burn to get to a orbit for LOFTID trajectory. Then they did a transfer and deorbit burn. So after the deorbit burn, we're on our trajectory to reenter, and the Centaur reorients us, and the payload adapter is separated. Then LOFTID inflates while we're still attached to the Centaur. The Centaur then orients us and spins us up, and it only spins us up to 3 RPM, so that's the actual spin rate you see there. And then separates the reentry vehicle where it goes on its ballistic spin stabilized reentry. After the entry, we eject a data recorder because we could not guarantee we would recover the reentry vehicle. Then we deploy parachutes and splash down for recovery. And one thing I want to point out here is that this animation was made over a year before we launched. And then I'm going to show you a video of the actual launch, and you can see how they compare. So before I show that video, one other thing I want to mention is that we had cameras around the aft segment, 6 cameras or 6 camera pods that included visual cameras and IR cameras on each pod. We also had an uplook camera looking aft of the vehicle. So we got a good view of the reentry plume behind the vehicle, a full 360-degree view of that plasma coming back and trailing the vehicle. We also got some footage from the Sci-Fly team who, in a very last-minute sort of situation, were able to track our entry and track it from an airborne asset off the coast of Hawaii. And we also got some footage from the recovery ship itself, where we had an infrared camera that was tracking us under parachute. So you'll see all that in this video. And I'm just going to play it. I might talk a little bit, but I'll try just to let the video speak for itself. So that's the release of the payload adapter canister. And that went flawlessly. That initial deployment is not inflation gas that makes it deploy. It's just the entrained gas and that we're in a vacuum and the strain energy pushing it out. But now it is inflated. And this is the separation from the Centaur, looking from a camera front on the Centaur looking forward and a camera on the vehicle looking back. That's the Sci-Fly imaging on the left there showing LOFTID reentry. That's the image from the recovery show. So I've seen that video hundreds of times, and I never get tired of looking at it. So yeah, it was a remarkable success. It flew with remarkable stability throughout the hypersonic and supersonic, transonic, and subsonic regimes before it deployed parachutes. We gathered a lot of science on board. We had a strong instrumentation suite, including, I'm not going to go through each one of these items in detail, but we had instrumentation in the nose, pressures, TCs, heat flux gauges, and a fiber optic sensing system. We also had load cell clevis pins underneath the nose where the straps of the inflatable structure came into the center body. We had a lot of internal instrumentation. Unfortunately, we did not record a lot of that instrumentation due to a network error. One of our boxes came up and could not find a location on the network. It was a problem that was masked in our ground testing for some other necessities that we had to have hooked up at the time, and those masked the problem of not finding a location on the network. So it worked every time on the ground and then did not work in flight. So we did not get, unfortunately, we did not get our inertial measurement unit data, our GPS data, or our inflation system instrumentation, other than a minor part that was routed through a different box that did find the network. So we had to perform a lot of extra detective work to try and reconstruct the flight without that instrumentation. We had lots of video imaging. Every item you see in green were things that were more than we could have expected. The items in blue are where we had issues. We had a known issue on one of the six visible cameras where we knew it did not work prior to launch. So we had 300-degree instead of 360-degree view of the aeroshell and visible light. We had 360-degree view in infrared light because all 12 infrared cameras were working. And the uplook camera provided a lot of imaging and invaluable diagnostic tools for us. So the big lesson here is if you can get cameras on your flight mission, do it. They are very helpful. It's an intangible measurement. But when you're trying to figure out what you're doing and trying to synchronize events, cameras really help a lot. And then for the data recovery, we had the comprehensive data set recorded on board, and that was recovered with the RV. Because prior to the flight, we could not guarantee how long the RV would float, what the sea state conditions would be. We were a secondary payload, so we did not have a say on when they launched. So, if we came down in a hurricane, we might never recover it. So we also had a ejectable data recorder that we guaranteed would float for at least a month and send home a signal for us to recover it. We did recover that as well, but it turned out it was not needed because we had the more comprehensive data recorded on board. We also had a beacon giving us a real-time data set. That did not connect to the Iridium system as well as we had expected. It turned out that the constellation was in a configuration at the time when we launched. There was a delay in the launch window where we launched closer towards the end of the window, between the middle and the end of the window, versus right at the beginning of the window. And that happened to put the constellation in a configuration that was not ideal for getting a link. So we did not get those links until after we were basically coming down vertically after the entry. But we did get 9 data packets from that, and we're use that data in reconstruction. And then we got the recovery of the RV itself. So we've been able to inspect the actual aeroshell physically, and it's here at Langley now. So for the pressure pulse, we did have the pressure gauges on the nose, and we noticed an interesting plateau in the dynamic pressure shortly before we got to peak pressure, and that plateau lasted for nearly 10 seconds. We are still doing some deep dive work to investigate exactly why that was there. There's some different theories about potential lower density area in the sky or something else. We're looking at what those causes could be. But we know it is a real plateau. We measured it also in the load cell pins of the straps. So that load did get relieved on the aeroshell during that time. And then it spiked back up going towards peak pressure. Again, we showed remarkable stability. Chris Galgard will go deeper into this, but one of the interesting items on this is that we were initially flying about 6 degrees angle of attack, and then it dropped closer to 0 degrees angle of attack right around that same time where we had that plateau. So we're trying to resolve, what caused that and what's physically happening there that made it fly that way. But it never exceeded 10 degrees angle of attack, even subsonically. So it was very stable. And then thermal response, we showed good correlation with our predictions. And this model here that you see is a uncompensated thermal model. So this was the pre-flight predictions versus the dash lines, which are actual measurements, showing that we have a good understanding of the physics in depth through the FTPS. Additionally, in the meantime, we've done a compensation of that model for the initial conditions. You can kind of see at the lower left where the starting temperatures of the actual flight were lower than what the model was using because we had to use the worst case hot scenario for the model. So when you account for that and those initial conditions, it agrees even better than what you're seeing here. And then we had the imaging of the uplook camera looking back at the plume. We're going to get some science from that. And, we didn't know exactly what to expect before the flight, but this was tremendous images after the flight. And when we recovered the aeroshell, we were able to get that camera data completely. So from left to right, you're seeing us go through the central part of that image shows the 360-degree plume. And there's an interesting point at which this orange color changes almost instantly to a purple color. It all happens within 1 second. And we're going to get some science out of that. That's also part of our deep dive forward work, is understanding exactly what's causing that color change. That was before we even got to 10% peak heating. So it was just an interesting part of the atmosphere we were flying through, or something on the aeroshell causing it to change that color. And that's what we're going to investigate. So in conclusion, this is a quick summary, but LOFTID was a tremendous success. First, we did no harm to the primary mission. It went off without a hitch. LOFTID was powered off until after the deorbit, and everything worked fine after that. And we demonstrated a HIAD in these extreme conditions at scale. And so it successfully met or exceeded all the requirements for the technology. The FTPS and the inflatable structure both performed well under extreme environments. The surface temperatures got up to 1500 C, and this 1100 kilogram vehicle saw 9.5 G's peak deceleration, and everything looked nominal the entire flight. And so we gathered extensive flight data that's going to help us correlate to our physics-based modeling and help us predict how these aeroshells perform in the future. So this technology enables larger and bolder missions and perhaps human exploration of Mars. And as you see in that lower right-hand picture, that's just a portion of our team who could make it that day, but there are hundreds and hundreds of people who made this possible, and I can't thank them enough. It was a tremendous success for NASA and for Langley. And that's all I have.
All right. So my name is Rohan Deshmukh. I was the LOFTID lead flight mechanics engineer, and I'm going to be talking a little bit about the flight mechanics analysis. As you can probably see, a lot of these talks are through, we presented AIAA SciTech. So I do recommend we can provide the SciTech paper numbers for folks who want to kind of see more technical side of it. So, and for the sake of time, because we got 2 more presentations, I'm going to kind of speed it up on my end. Okay, so John already presented the background, so I won't go into too much detail into it. So you saw that it launched on November 10th. It was a successful inflation of the largest flown aeroshell diameter to date, 6 meters, and then it had a successful entry, descent, and landing sequence, splashing down about 2 hours after launch. So this talk is going to primarily focus on the flight mechanics analysis in the region that is boxed in red here, which goes from our RV separation, our reentry vehicle separation, all the way down to splashdown. And the goal is we want to basically model the LOFTID's trajectory as it conducts EDL all the way down to splashdown. So how we did that is we utilize a tool developed at NASA Langley here called the Program to Optimize Simulated Trajectories. And the idea of this tool, you might have heard about it before, is that we use this tool to aggregate various subsystem models to model the physics of basically flight during EDO. So we take things such as our atmosphere model, which I'm going to talk about a little bit in this talk. We include things like basically what is our attitude that we separated out. So we get that information from ULA when they separated to give us basically what is our initial state. Think of it as what is our initial state, so we can basically then rerun a trajectory prediction to repredict where are we going to land. So this is just an idea there, and then I linked some of the AIAA papers that talk about some of these models, such as like the atmosphere model and the aerothermodynamics model, for folks who are interested in learning more. So prior to basically launching, we did the flight mechanics team did a pre-launch trajectory analysis, and what the objective of this analysis is we wanted to understand what are the range of potential trajectories that we might see during the 36-minute launch window that you can kind of see in the bottom right. So what we did is we worked with the OLA, and they provided us basically 3 sets of initial separation states that we used to propagate our trajectories. One at the open of the window, so that's the blue right there. So think of that as 18 minutes prior to the middle of the window. We have the middle of the window, which is the red, and then we have the end of the window, 18 minutes after the middle, shown in green. So keep these colors in mind, and the idea is we want to just basically understand what is the predicted trajectory space look like, so that'll help us inform decisions on how we need to set up our recovery of LOFTID. So what this figure is showing here is a plot of our splashdown prediction. So remember, this is prior to launch of where LOFTID was anticipated to land between the open, middle, and closed windows. You can see in the colors there. And you can generally see that the prediction is that LOFTID is going to land about 375 miles off the coast of the big island of Hawaii in the Pacific Ocean there. And you can kind of see here, you can see there's some variance in the window of where it might land. And it's important to kind of keep that in mind so that we can understand the region where we need to situate. Robert will talk later in this set of talks. We'll talk about the recovery operations in a little more detail. But this is a delivered product I'd give to Robert, the decision making for recovery. So let's talk a little bit more about the trajectory. So this is a really high level condensed summary of some of the key metrics and what are some of the differences between them. I'd recommend you look at the paper, for a little more technical side, more detailed side of it. But the general idea, the main takeaway I'll kind of take from this is that the launch window affects basically the mission timeline. Think of that as how long basically from separation to splashdown do the sequence of events occur. You can kind of see here that for example, the elapsed time from RV separation has some variance based off of where we launch in the window. And why is that important? It's important because that helps us tell where in our mission timeline do we predict key events to occur, such as peak deceleration. When does the data module, the ejectable data module that John talked about, where does it occur in the trajectory? And then where do we predict parachute deployment to occur? So the notional idea of this is that when we're basically doing operations, we're sitting in front of a mission console. We have a timeline. We're working on a timeline. We know basically where things will predict, so we can call them out and tell our team, okay, this is where parachute deployment occurred. And then, in an ideal world, if we had basically live telemetry, we'd be able to confirm that. So that kind of helps us during operations. And I do want to keep in mind, I look fairly young, right? So this is my first flight project I worked on. And I think it's a really useful skill, especially for early career folks to work on and experience working on a flight project, because it's a completely different ballgame than your traditional engineering, where you're actually working on a project. You have to think like an engineer and you got to kind of make predictions on the fly. So having this information really helps you try to inform decisions. Okay, so I'm going to try to transition to, we did all this pre-launch trajectory predictions. we did some analysis on how do we basically transition to operations. What are some improvements that we can do to our trajectory predictions that can help us pinpoint where LOFTID will land on the day of launch? So what we analyzed in the 3 months prior to launch is we improved our prediction tools by integrating a forecast atmosphere model, which we'll talk about in the next slide, and we incorporated trajectory automation. And you can kind of read in the main takeaway bullet point is the idea is that this will help us improve our trajectory predictions. So the first thing I'm going to kind of briefly give a high-level summary is on atmosphere forecasting. So up to this point, we've been using this engineering model called EarthGram, Earth Global Reference Atmosphere Model, and it's basically think of it as like an engineering model that provides a historical aggregate of the atmosphere around a certain region of interest where we're predicted to land. So it's a pretty good model for pre-launch analysis. However, if we want to get the day of launch uncertainties, the day of launch, basically what is the forecast, we want to incorporate forecast models. So we incorporated the Goddard Earth Observing System, GEOS-5, to provide us the day of flight weather forecasts. And I do want to keep in mind that there's been few flight projects such as Aspire that have used this GEOS system, and it's shown to prove fairly well when it comes to improving the prediction of where splashdown will occur. And what I'll show on the next slide is just a preview of how this actually helped us during LOFTID. So what you can see here on this figure here is a plot that shows basically these radial contours, these distances away from the actual LOFTID splashdown point. And what you can see here are basically two sets of colors. You have the blue colors, which are from our GEOS weather prediction, and the orange lines, which are from our EarthGram prediction. So had we used the EarthGram prediction and used that, I would have told Robert basically to go where the black X is, X marks a spot. Then Robert would tell me, geez, Rohan, we're 20 nautical miles away. Your predictions suck. But the point being is that you can kind of see here with the GEOS prediction, we are pretty much within 5 nautical miles, if not closer. I'll give an exact number later on in the talk. But the takeaway from the slot is that by using these day of flight weather forecasts with GEOS, this can help pinpoint the prediction of where a entry, descent, and landing mission like LOFTID will actually land. So this is a really useful tool going forward for flight operations 3DL missions. So the second phase of the analysis was trying to automate the trajectory analysis. And what we utilized is a tool called Jenkins to basically script our trajectory analysis. So the idea is basically, this is a dashboard of Jenkins. I'm going to kind of walk through what this is. So the idea that why do we want to automate our analysis? The reason we want to automate it is think about yourself during operations. It's a very time intensive, you're in crunch time. And if things go wrong, you don't want to fat finger a number and mess something up and send a wrong prediction. So what we wanted to do is we wanted to automate as much as we can to help eliminate human error that might be present during operations. So what we utilized here is a script to basically automate running our Monte Carlos with the weather forecasting model that I talked about with GEOS-5. So we developed is a automation where we daily check out the GEOS forecast every single day. And the idea is the weatherman will give you a 72, 48, or 24-hour forecast. So, the Friday, Saturday, Sunday prediction. Actually, today's Thursday, right? So this is the weather forecast for Friday, Saturday, Sunday. I didn't intend that. But think of that as the weather prediction. Think of the weather prediction for Friday, Saturday, and Sunday. Then we would take that and put them into atmosphere tables that we would integrate into our post simulation that we would pretty much run on our lab clusters in parallel, and we'd generate a results package that we would then send to basically the parties of interest to basically show this is the prediction using the 48, 72, and 24-hour forecasts. And we would keep doing that pretty much constantly to the day of launch. And what this would allow us is during the day of launch, we received the orbital parameter message that I talked about. This is what ULA gave to us that, okay, this is what LOFTID separated at. So we take that as our initial conditions along with our GEOS profiles, and we can then basically automate the run. So we can do more important things like do NASA TV interviews, right? That's me, right? So think about that, right? You can do that while the sim's running. That's every engineer's dream. Slack off at work now. Okay, so basically what happened during the day of launch. So Chris Cargard, who's going to talk next, will talk more about the trajectory reconstruction process. And what I'll show here is basically a preview of that with the ground track. So you can see here, you might have caught that in John's video. So LOFTID separated over the Sinai Peninsula on a retrograde orbit. And it basically, it entered the atmosphere at 125 kilometers right off the coast of Hawaii in the Pacific Ocean. Figure on the right is a little zoom in plot, just kind of zooming in on the EDL sequence. So you can pretty much see that it's pretty much a ballistic trajectory all the way down to where it splashed down about 325 miles off the coast of Hawaii. So this plot, it's very complicated, very, I wouldn't say complicated, but very busy. But the main takeaway of this plot is just kind of showing you what happened during the day when it came to recovery. So what this figure is showing is basically those same radial contours of the distance away from where LOFTID actually landed from our GPS data that we received, and basically where the recovery boat was. So you can see the cyan color lines is the ground track of the recovery boat. So initially, prior to launch, the recovery boat actually went into the center of the pre-launch predicted ellipse. But due to the fact that our launch window slipped and we were launching between the middle and end of the window, the decision was made to move out of the ellipse. Robert will talk a little bit more about that. So you can kind of see the cyan X. That's where the recovery boat was sitting when LOFTID re-entered. And then basically when LOFTID re-entered, the recovery boat was able to actually take this picture off the infrared camera, and what that kind of showed is just how close LOFTID's actual trajectory was from where the trajectory prediction that informed where the recovery boat should sit occurred. So basically, I call that, that's where all the hard work pays off when you go into operations and doing all this analysis. And then what this ultimately ended and allowed us to do is to basically make these videos of showing just how quickly we're able to recover the LOFTID recovery boat, and these trajectory predictions really facilitated that process. And then that's the LOFTID RV just a few hours later, already in our recovery boat. So the takeaway from this talk is that, LOFTID was a success. I'm not going to repeat it again, but basically our pre-launch trajectory predictions helped us inform decisions going into operations. Integrating of the atmosphere forecasting models was an invaluable tool that allowed us to improve our trajectory predictions. And I'll kind of leave it at that and kind of preview it to Chris Clargard's talk. So since we landed off the coast of Hawaii, mahalo for listening to my talk.
All right, hello everyone. My name is Chris Carlgard, and I'll talk to you about the trajectory reconstruction of the LOFTID flight test. So, of course, we already know that LOFTID was a successful flight test of a HIAD back in November of 2022. And anytime we do a test flight of a new type of vehicle, we typically ask ourselves, how well did this vehicle perform relative to our predictions? For example, for a HIAD, you might be interested in knowing what was the ass flow and drag coefficient, for example, compared to the predictions. And so the first step in the process is something called trajectory reconstruction, where we take all the different measurements from the flight, like IMU, GPS, radar, atmosphere data, and throw all that stuff into a Kalman filter, and out pops the trajectory, atmosphere, and aerodynamics of the vehicle. And that's what this talk is about, but not really. So, like John mentioned, we lost the IMU data, all right? And the IMU for trajectory reconstruction, that is the most critical measurement for us, because that's telling us the acceleration and angular rates during the flight, which you can combine with some initial conditions, and then just integrate that forward through time, and that tells you the position, velocity, and attitude with respect to some inertial frame. And then you can combine that with some observations of the atmosphere to get density. And then density combined with velocity tells you dynamic pressure. Dynamic pressure with accelerations and rates tells you the aerodynamics, and then you're done. We can refine that with things like GPS and radar, but really without the IMU, we're stuck. So now the trajectory reconstruction process kind of became more like an Easter egg hunt, where we're digging around through all the different data sources that we did capture to try and piece together snippets of how the vehicle actually performed. And so some of those data sources we have include the atmosphere, And John mentioned we had pressure sensors on the nose cone that function like a flush air data sensing system. We had some photogrammetry that John also touched on, and there was some locator beacon GPS position of velocities below 18 kilometers, which doesn't help us much with reconstructing the hypersonic performance of the vehicle, but at least it's kind of something to compare to. And generally, post-flight analysis, we kind of group into two broad categories. First of which is the reconstruction process, just to figure out what actually happened. And then the next step is what we call reconciliation, where we take our trajectory simulations and update that with observations of the day of flight type things and compare that with the reconstruction and see if it gets closer or not. And so without the IMU data, we can't construct an ASFlow and aerodynamic database to update the trajectory simulation with. So all we can do is just kind of update it with the day of flight atmosphere models and the what's called the OPM, the orbital parameter message, which is the truth state at the RV separation to tell you the initial conditions. So now we'll just kind of step through all the different data sources that we did have available to work with. First of which is the atmosphere. So Rohan mentioned the GEOS 5 atmosphere model that does predictions that were used for there's forecasting that was used for the trajectory predictions. GEOS also produces a data set that's called reanalysis, where they take observations from that day and go back in time and then update what the forecasts were based on different observations throughout the world. And the GEOS, it's a global atmosphere model and different grid points in latitude, longitude, and altitude. It typically goes up to between 60 to 65 kilometers. And above that, we kind of spliced in a 76 US standard atmosphere to go up all the way to like 125 kilometer range. And there's some comparison plots there on the right side showing just one component of winds and the density compared to the forecast and the Graham model. So in terms of nose pressure measurements, we had 5 pressure transducers installed on the nose. One was at right smack in the center, and then there were 4 others clocked around in 90-degree increments on the nose cone. So you can think of the nose cone as kind of acting like a 5-hole probe kind of thing. And the idea is you can take measured pressures, combine that with a model of what the pressure distribution is on the nose cone, and solve an inverse problem to back out what the atmospheric relative trajectory is from those measurements. So you can calculate things like dynamic pressure, angle of attack, and those sorts of things. So when you do that, you get these results. On the left side is a plot showing the total angle of attack in blue and the dynamic pressure in red. Like John mentioned, there's a kind of an interesting feature or that plateau area in dynamic pressure just prior to the peak dynamic pressure. My personal theory is that could be a density pothole, like a little bucket in the density profile, which is not a new thing. There was a bunch of space shuttle flights that saw that. We saw something similar on RB3, and we also saw something similar on the low density supersonic Decelerator project. And it's all roughly in the same altitude range, kind of 50, 60 kilometer range. Anyway, so we're going to look into that in more detail. And also, it's interesting that the angle of attack was kind of trimmed up to about 6.5 degrees just prior to that. And then after that, it dropped back down to near 0. So that that bump, if you will, caused a change in the trim angle of the vehicle. And so that's something we need to look at in more detail. And then if you take, without the IMU, I can't tell you the ASFlow and aerodynamics of the vehicle, but if you do take the nominal air database and combine that with this dynamic pressure, you can compute a drag force that was about 100 kilonewtons and the peak deceleration of about 9.5 Gs. Lastly, on the right side is the angle of attack and side slip and the aerodynamic clocking angle. The aero clocking angle was about 122 degrees, and I don't have a video of this, but that is consistent with some wake video observations that were taken from some of the camera data. Okay, so next, this really was an Easter egg. So John mentioned the cameras that were on the vehicle. These were intended to just look at the heat shield and just watch it, inflate and see how it performed just visually. But interestingly enough, the cameras also captured the Earth and the Moon in the images. You can see on the right side, that little speck right there, that's the Moon. And of course, on the left side, you can see the limb of the Earth. And so those two vector measurements is coincidentally all you need to uniquely define a vehicle attitude. So that we can extract two vectors. The Moon vector was extracted very easily because you can see the whole entire Moon. So the center of the Moon is just this center of that little blob. The Earth vector was a little bit more complicated because you're not seeing the entire Earth in the image. You're just seeing a limb of it. And so to construct an estimate of the center of the Earth, what you do is you fit a curve. I don't know if I would, do I have a laser pointer? I guess not. But anyway, you can kind of construct a curve there that captures the limb of the Earth, and you put a bunch of points along that curve and put line segments in between them, and then construct perpendicular bisectors that all point down into the center of the Earth. And then the average point is, we call that the center of the Earth. And that's the second vector measurement. And these two vector measurements were combined or were put into a Kalman filter to estimate the attitude and angular velocity as a function of time along the trajectory. Here's a video. There's the Moon going by. And then in a second here, the Earth is going to come and you're going to see the bisectors that are constructed from that. So the center of the Earth, of course, is off frame, but you get the idea. And here comes the Moon again. And there's the Earth. So now from those measurements, we were, like I said, we put that into a Kalman filter to get the attitude and angular velocity. The reconstructed attitude, the quaternion is shown on the left. So of course it's oscillating. And then in the middle, there are the three components of angular velocity. On the right side is the trajectory simulation. And what's interesting is the reconstructed, if you look at the third component, that's basically the spin rate. It's reconstructed to be 17.7 degrees per second, where our nominal was 18 degrees per second. And so that's pretty good. And this work was actually done by an intern, Anthony Fine. And we did not tell him the nominal spin rate when he did this data. So he came to me and said, well, I got 17.7 degrees per second. I was like, okay, that's about right. So that was good. Oh, and then we made an animation of that from the reconstruct. The Earth isn't quite lined up correctly in the image on the right, but this is kind of just for fun. But anyway, you can see the animation. It's kind of got you can see it spinning. And maybe a slight wobble to it. But anyway, that was kind of neat. Okay, and now moving on to the trajectory reconciliation part. Oops, I forgot to update the numbers. Anyway, so the trajectory simulation was, of course, described in Rohan's presentation just before mine, where he talked about the pre-launch trajectory based on the forecast, the 24-hour GEOS forecast. We went back and did two updates to that, which were called the best predicted flown trajectory, version 1 and version 2. Version 1 used the post-flight GEOS reanalysis atmosphere that I talked about earlier. And then the second update to that was with the orbital parameter message, it gives you a separation state. And then we did another version of that where we tried to splice in a FADS-derived atmosphere from the dynamic pressure that was reconstructed from the pressure measurements. And so talking about the FADS density profile, so this is where you run into some circular logic. So the FADS reconstruction, of course, tells us dynamic pressure as a function of time. In order to get density, we need a velocity. But since we don't have an IMU, we don't have velocity. So we just, what else can you do? We take that velocity from the post simulation, and you can get density versus time. But to put that into a simulation, we need altitude, which we also don't have because we don't have the IMU. So we just took the nominal post altitude. So that gives you density versus altitude, which you can then put into the simulation. And then that density versus altitude is shown on the lower left, where the FADS curve is kind of the bluish color, and that compares to some of the simulation data, and by and large, it actually lines up pretty well. And on the right side is the angle of attack history. Of course, the FADS solution was getting up to about 6.5 degrees just prior to that bump in density. And that, just updating it to the density does not explain that behavior. So that's going to be further work to investigate why we're trimming at 6.5 and then dropping down close to 0. Now we can actually show that the FADS drive density, when you put that back into post, it does kind of replicate that bump in dynamic pressure that we saw. But again, because the logic is a little bit circular, because we're taking a nominal velocity from the simulation to compute that density profile. But once you put that back into the simulation, that velocity doesn't match. So it does not capture the peak dynamic pressure, but it does kind of replicate some of the behavior by and large. And then I mentioned earlier, we did have some locator beacon data below 18 kilometers. And we just plotted up some comparisons with the post trajectory simulations, and by and large, they line up pretty well. And at lower altitudes, we're seeing a velocity of around 8 meters per second down to the water. So anyway, in summary, we didn't get the IMU data, and that kind of makes our usual approach, it's not possible. And so we did mine through all the different data sources as best we could to kind of get different snapshots of how the vehicle was performing. And a couple noteworthy things, again, there's potentially the density pothole, and the trim angle attack behavior is something we're going to look into in more detail. And the attitude estimation from the video, that was really an Easter egg. We would not have done that if we had the IMU. I mean, I would rather have had the IMU, but we did get to learn a few things about photogrammetry, and so that was kind of fun, actually. Anyway, I guess that's all I had. Thanks.
Hey, my name's Robert Dillman. I put a bunch of co-authors on the paper for all those who were out on the recovery ship with me and involved in other aspects. There were many more, but we couldn't fit them all. So we have this set. Mission overview, Isha John's introduction. So I'm going to, only note a few things here. The one is that splashdown was 2 hours and 5 minutes after launch, and that'll come important in one of the upcoming charts. But here I'm talking about the recovery design elements, some of them used to future missions, and how things went on the day of flight. So again, the concept of operations and the rectangle around the part we're talking about here, splashdown and recovery. Major points in there, since we weren't the primary payload, as John said, we didn't have control over the splashdown conditions. And also the sun synchronous orbit of the weather satellite meant we would splash down east of Hawaii at about 2 a.m. in the dark, and had to accept and plan for the possibility of bad weather. So LOFTID was powered off until after delivery of the weather satellite so that we couldn't interfere, and then inflated while attached. Centaur deorbited us and spun us up. So the flight data to show the reentry performance was critical to mission success, as John mentioned again, but we unfortunately didn't have the bandwidth or power to transmit it up through TDRS or down to the ground, etc. So we recorded the flight data on board and also included a buoyant ejectable data recorder that got released after reentry and was hardened for 30 days. The RV also had a GPS locator for the same recovery location, and the parachute slowed it down to about 13 miles an hour. Either one of those would have been sufficient for mission success. We grabbed the RV first since it had a risk of sinking and would allow us to inspect the flight materials, which was a big plus. So other items in the recovery world, the parachute included a saltwater release switch So when it's submerged, it would sever the parachute canopy so it can't drag the RV around. And it cut off most of the parachute risers, but left about 20 feet length so that we could use that for lifting it out of the water. The cameras had lights that stayed on through splashdown, and they added 4 blinking aircraft collision avoidance lights to help us locate it in the dark and in bad weather. And the locator beacons, in addition to the signals it was sending through Iridium, they also transmitted through the LoRa protocol, which is radio frequency. It's direct line of sight. The Iridium system has a lag of up to 5 minutes. The line of sight gets rid of that. And we brought several LoRa relays on board the ship that were launched on weather balloons so that we could detect the signal further away than what we could see with the antennas on the ship. The ship was rented by our partner, United Launch Alliance. We had evaluated several ships from usual folks we worked with, Coast Guard. They also looked at NOAA and University of Hawaii, but most of them don't have a big open space, 20 feet by 20 feet on their deck. So, but we found a offshore supply vessel that had basically a large flat cargo deck and a crane to lift equipment on and off. That did great for us for recovery. Down at the lower left, you have a close-up picture of the aluminum stand we built to hold the reentry vehicle once it was on the ship. The one downside is it has a 10-knot cruising speed. So given how far away we were splashing down and the fact that it's based in Honolulu, we had to leave port 2.5 days before launch. And after we recovered it, another 2.5 days to motor back. And while 220-foot ship is a big ship, when you're in the Pacific, it's a lot bigger than you are. And when you're in a hurry to go somewhere, you can't steer around to be nice with the waves. So on the way out, during part of the trip, the waves were coming in sideways and the ship was rolling quite a bit. But hey, we made it. So for monitoring the vehicle in flight, we had the video camera that John showed on board the Centaur. Unfortunately, that had about a 15-minute downlink lag. And after the Centaur released us, the Centaur transmitted the orbital parameter message saying, here's the updated trajectory that it had released the payload on. And just after we got released, we started transmitting GPS data, again, through that Iridium small data burst, has a slight lag. We included data in that signal so that the RV would let us know that, yes, it's vented the nitrogen tanks. They're no longer pressurized. It's going to be safe to approach. It fired all the pyros. We don't have to worry about any of those or the spring-launched ejectable data recorder. And after sending those confirmations, the real-time beacon gets powered off. And the hardened one that has the 30-day life gets brought on because our onboard batteries are likely going to get submerged in salt water. Which doesn't do good things for the electronics. Sci-Fly had the airplane that John mentioned circling with 7 different science instruments, radiometers, spectrometers on gimbal mounts to track the vehicle, and got the great video with time-resolved imaging and spectrometry. And had we needed it, they were also available to help locate the RV in the water. So the splashdown ellipse, about 57 miles long by 11 wide. It may have been 375 miles from the Big Island, but it was 550 miles east of the port of Honolulu, where the ships are based. And you also have to be a bit flexible in working with the different groups because, you know, the orbits are done in kilometers and the ships work in nautical miles, and the ellipses were given to us in miles. And, you know, you make sure you have the units when they give you a number, and that all worked out. Just something to be careful with. And as Rohan mentioned, the ellipse got updated regularly as launch approached. You have the atmospheric uncertainties are obviously larger the further away it is. So the 3-day prediction has more uncertainty than the 2-day prediction has more uncertainty than the 1. So the ellipse was shrinking slightly as we approached launch. And then with that orbital parameter message that came out, that was allowing us to remove the uncertainties of the launch, which, can send the rocket slightly off in other directions. The Centaur debris plotted down at the lower right in the blue, the Centaur upper stage is deorbited and burns up into pieces, most of which don't survive to reach the ground. But we were concerned since there were people out there on a ship. Most of us on the ship, I think, would have been perfectly comfortable staying in the ellipse. But the agreement we had was that 1 in a million odds, if we had launched at the start of the window or the end of the launch window, we would have had less than 1 in a million chance of the recovery ship being hit by any of the debris. So we initially went out and parked at the center of the ellipse. Unfortunately, we launched more in the middle of the launch window, and the odds went up over 1 in a million. So we repositioned the ship. I guess the ellipse is 11 miles wide. We moved it 6 miles off to the west, so to stay out of the footprint. It did slightly increase the amount of time it took us to get to the vehicle after splashdown, but again, you have to be safe to certain agreeable levels. So off nominal conditions. Fortunately, we didn't have to deal with any of these, but we had planned out, well, if we have bad weather or rough seas and it splashes the vehicle full of water, we can lift it at an angle and drain the water out. Or if it's nose up for some reason with the parachute lines hanging down, we can reach underneath it and get the poles out, reach underneath the vehicle and pull the riser legs and flip it right side up. So on the day of flight, we were pre-positioned at the splashdown site and we watched Atlas launch through the Starlink terminal. It's an awesome launch to see. And well, like I said, due to the late hold, launch was in the middle of the window, had to reposition. And we were expecting, as we're going through our timeline, saying, hey, we ought to be hearing from the real-time beacon as to where's the RV coming. But unfortunately, we didn't right away. And well, after a few minutes of biting our fingers, we got the video downlink from the Centaur, and it showed it inflating and releasing beautifully. Turned out, like John mentioned, there had been well, with the final launch slip and the vehicle flying where it did, we were in a position in between the Iridium satellites. They're designed to give good coverage to things here on the surface of the planet, even the tall mountains, but they don't guarantee coverage when you're, 150 miles up in the sky. In any case, the footprint from the Centaur was giving us a even smaller splashdown ellipse. But unfortunately, that update came in through a specialty subroutine that had been written, and at the time we didn't realize there was a typo in it. So folks gave me the update and said, yep, it'll come down 200 miles south of where you're waiting for it. And we said, well, are you sure? And oh, yes, we've run the numbers. It does seem strange, but we ran them again and checked and double checked and okay. Well, splashdown's imminent and it'll take us 20 hours to get there with our 10-knot recovery ship. So we waited on site, and about 5 minutes later, started getting the real-time beacon signal saying it was very close nearby. With the ship being moved further west, splashdown was about 10 miles from the ship, but only about 6 miles from the center of the originally predicted ellipse. So, as Rohan mentioned, was dead on. Had been staying there with all the earlier predictions, just that last one kind of threw us. So We got really lucky on the day of flight. The weather was excellent, calm seas, clear skies. So with the GPS now providing a direction vector, we're able to say, okay, it should be over that way, and actually see it coming down in the sky 10 miles away, brightly lit and slightly flashing with the collision avoidance lights. And the IR camera had been searching around and tracked in on it as well. We got great images of it. And navigation of the ship, instead of saying steer for this GPS, it was okay, go get that light. And they steered right over to it. John showed you the video, which is more impressive than these few stills that I have captured, but it showed the RV coming in under the parachute, and the RV did briefly go over the horizon. It splashed down, and then the parachute collapsed once it didn't have load on it. But as the ship motored closer, you could see the RV coming up. And there's a picture of that with the RV in the water. That was a really, really great day where we looked at it, and from the ship, you couldn't tell that it had re-entered. It looked like we had just inflated it and set it out there in the water with our crane. It was floating high and dry above the water, didn't drown out the batteries, the lights kept flashing. So in any case, we, three of us went out with the pilot from the ship's crew in the small boat, and secured the vehicle, parachute riser legs, put them on a lifting ring, brought it back to the ship, and they craned it on board. So then, with the RV on board the ship, we headed for the EDR's GPS coordinates and waited until daylight so we wouldn't risk running over the little 4-inch yellow floating recorder in the dark. I mean, we knew GPS wise where it was, but it's still a big ocean. We'd practiced recovery, actually in the Atlantic with a borrowed Army ship, and as well on one of our earlier ship trips in the Pacific before the original launch was scrubbed. On our way back, we're like, hey, let's throw this in the water and try tracking it down. The practices actually worked a little bit better than day of flight. On day of flight, we were at the GPS coordinates and had to go back and forth several times before we actually spotted it in the water. But at that point, scooped it out on our 30-foot pole, pulled it out, and took it all back to port. And as John mentioned, at that point, we had the onboard recorder that recorded data all the way to splashdown and through splashdown, since it didn't short out, whereas the ejectable data recorder had been kicked out at 19 or 20 kilometers. So in port, craned everything off the ship onto a pier in Honolulu at the University of Hawaii's Marine Operations Center, inspected and photographed the hardware, downloaded the data from the internal recorder and the ejected recorder, and pulled the video off the actual cameras, because they had uncompressed video recorded on board each camera instead of the compressed version that was that's stored in the separate recorder. Also, the upload camera wasn't wired into the recorder because it was a late add. So took that out, got its video deflated, packed everything back up, and shipped it back here to Langley. So both the RV and the EDR successfully recovered. Side point, it's very helpful to have multiple ways to locate the hardware, especially when some systems don't perform perfectly as intended. And even with our multiple practices and ground tests, flight tests rarely have everything go as planned. So those of you working missions, try to design for those contingencies and put in a little bit of sensor redundancy where you can. Like the hole in the sky bump, it's nice to have multiple sensors that can read the same event and say, yes, it's not a sensor glitch on that one system. You're happy, but be ready to adapt on the fly.